Okay, hello everyone. This is the fourth 2020 Zoom meeting in February 2024. And I'm happy that we have a great schedule. Welcome everyone, all the new participants, all the continuing participants. We prepared a great schedule for talks. And so let's see. I would like to share my screen so we can have a look at this. It's also available at the URL you see on top, Force 2020 org Zoom meetings, and then you go to the February meeting, which is the 42nd meeting that we have, which is a great number. And yeah, as you see, it's 1400 UTC more or less, and our first speaker will be Alexandre Dumont, talking about Alex Force and minimal formal computation. And I see Alex is with us. So Alex, if you want to share your screen and give your presentation, please go ahead.
Can you hear me?
Yeah, we hear you very well.
Okay. So let me share my screen. Okay. Share.
That works out fine.
Okay. Trying to remove this. Okay, can't. Okay, so hello everyone. Today I wanted to share with you some things I've been working on. It was at the end of the year last year, and it's about minimal formal computation. I implemented it in Alex Force because I didn't manage to do it in other Force. And it's about SKI combinatory calculus. Let me remove this here. Okay, so how it all started? Well, it all started in July 2021. I had finished to implement Alex Force, and I was looking for new challenges. So I asked openly on Twitter, and somebody suggested me to try SKI calculus, which I had never heard of. So he told me it was something related to lambda calculus, which I didn't know either. But when I started to investigate about this, turns out it was quite interesting. So what is SKI combinatory calculus? It's a combinatory logic system, so it's related to mathematics, and it's also a formal computational system. It was introduced by a German-Russian guy in 1920 called Moses Schoenfinkel, and it was further redeveloped by Haskell Curry in 1927. You might know Haskell Curry from the Haskell programming language. It tends to be the first, and it's also minimal formalism for universal computation. And it's quite relevant in the mathematical theory of algorithms because it's an extremely simple Turing-complete language. And it can also be seen as a reduced version of the lambda calculus, which was introduced in 1936 by Alonzo Church. So the same year as the Turing machine from Alan Turing. It was in 1936 also. And if you see it, both lambda calculus and Turing machine, Turing complete languages came 16 years after the SKI combinatory calculus. So let's have a look at some definitions first. So what are combinators? Combinators are higher order functions with no free variables. So there are functions that take one argument, which is also a function, and they return an output, which is also a function. In short, we'll define a second concept, which is the application. So far, combinators are function. They take function as argument. They return a function. So everything is a function. And applying a combinator to an argument. So for example, combinator f to an argument x is called the application, and it's written fx. Something important to to notice is the application, in this case, is left associative. So when we write f x y, it's f applied to x first, and then the result of x applied to f, which is also a function, we will apply it to y. So it's quite different from what we are usually used to. Well, here in this slide, we've got the whole definition of the SKI combinators. So it's very easy because there are only three. The first one is the identity combinator, and its definition is when it's I, you apply I to X and it returns X. So this one is quite easy. The second one is the constant combinator. It's written K, and when we apply K to X and then to Y, it returns X. We'll see later why it's the constant combinator. And then there's the S combinator, which is the substitution. And this one is a little bit more complex to understand, but it's F applied to F applied to J applied to X is equal to F applied to X, which will then be applied to the output of G applied to X. So that's the whole definition of the whole SKI combinators. It as an exercise for the viewers, you will be able to see that I can also be defined in terms of S and K. It turns out that I is equal to SKK. That's when you start playing with it, it's very easy to notice. So when we say earlier that SK and I form a Turing complete language, in fact, we don't need I because we can write it in terms of S and K. So S and K are the only building blocks that we would need to have a complete Turing complete language. So now let's have a look at how we can try to implement that in Forth. So the first approach would be to try with normal Forth word. The only difference is Forth is postfix. So, but let's have a look at. So we've got the application of a combinator. It consumes one argument. That seems easy because we have words that can consume arguments on the stack. Let's just try to put everything in a postfix notation. So let's have a look at the identity combinator. The identity combinator, let's put an argument X on the stack, then we run I and it returns X. So apparently we could say that I is like the NOP word, it does nothing. The second combinator, K applied to X applied to Y returns X. Let's put Y and X in reverse on the stack and then run K. And we expect to get X. So it looks like K could be the NIP word, which remove the second argument on the stack. But that's not so simple, in fact. Let's have a look why. So what turns wrong in the previous slide? Let's have a look at a slightly more complex example, which is the KI combinator. So KI combinator is K applied to I. K applied to I, we will apply that to two variables which are X and Y. So it's Ki of X and Y. And because it's left associative, it's Kix applied to Y. And we know that K returns always the first argument, so I. So in that case, that would leave us with IY. And because it's I is the identity combinator, we've left with Y. So Ki of XY is Y. If you notice, K of XY is X, K of XY is X. So K selects the first argument, and Ki of XY is Y. So Ki returns the second argument. So it's quite handy. Later we will see why. So now let's have a look at with normal words what will happen. So we put Y and X on the stack. We run I, and we've left with YX, and then we run K. We add YX and we run K, and it selects the first one. So we are left with X, which would be wrong because we expected to get Y. And so here are the issues that we are finding with normal worlds. The problem is, first, combinator, they only take one argument. So here we've got a problem because K can only see X on the stack. It can only play with the top of the stack. And so it wouldn't be able to drop Y. And the second problem is left associativity that we mentioned earlier. So the problem is here is when we did Y, X, I, I would be consuming X, well, it would not be consuming anything, it would leave X. But the problem is that it would be run first before K. And what we want is to run K first on I. So that's the problem. And to address that, we need a way to somehow delay the execution of the words. So that's the real challenge here. So this is how we can try to address the delayed application, the delay execution of the word. So here I'm going to introduce two things in parallel because they need to be introduced together. So first I introduce a word, which is the closing parenthesis, which means apply. So the definition is very straightforward. It's the word execute or exec in Alex Forth because it was shorter. And now we will need to use to specify the closing parentheses to really apply the word. So we will need to do yxk and then apply it. But the problem is that we need that k is a special word now. It needs to be a word that leaves an xt on the stack. So that's the trick. Now each combinator, when we run it, it will leave an execution token on the stack, and later when we apply it with the closing parenthesis, it's when it's going to be run. That's why I named this behavior the application behavior of K. So the runtime behavior of K would be to leave an xt, the kxt on the stack, and the application behavior, it's what we want the word, really the combinator behavior to do. In that case, the application behavior of K is to leave on the stack the xt of a new word whose application behavior will drop Y and push X back onto the stack. So if we have a look at this, if we put Y and X onto the stack, then we run K, which leaves the xt of K. Well, it leaves an xt. And then we apply it. This will consume X and return a new execution token of a new word, which encloses X inside it. So K must create a new word and leave the xt on the stack. And when we apply this execution token, it will consume Y and return X. So that it looks very straightforward at the beginning, but now it's turning quite more complex to implement this. I'm going to demo this mechanism to you right now. So for the demo, I don't have Alex Forth on real 6502. I'm running it in my 6502 emulator, which is written in GeForce. So I'm going to run my emulator. I'm going to load the sorry, Alex Forth ROM with the SKI words. Okay, so here we are in Alex Forth. And for the demonstration, I'm going to put, instead of putting combinators, I'm going to put 2 and 1 for Y and X onto the stack. So my stack is 2 and 1, and I'm going to run K. And as you can see, now on the stack, I've got my Y, my X, 2 and 1, and I've got an execution token on the stack, which is the execution, this execution token of, well, it's not the execution token of K, but the application behavior of K. And now I'm going to apply it. So it's going to consume X. And you can see now on the stack, we've got our Y, like before, and we've got an address. This address is the execution token of your new word that has been created. And when we apply this new word, it should drop our Y and return our X, which was 1. So let's apply it. Oh, sorry. And what we have on the stack now is 1. So it worked. Let's continue. So to be able to implement this in AXForce, I'm going to show how I did it. I'm not going to spend much time because I think it's the first part is quite implementation specific of AXForce. So I've had to create a couple of words. One is enter comma, which it's like starting a new definition in the dictionary without a header. So here I'm writing 4C, which is jump in 6502, and I'm compiling the address of colon. So really, this is going to leave a jump to call. And then I'm creating a new defining word, which I call func, colon func. And I will use that word to create new combinators later. You will see. And as you can see, it uses create. So the word that will be defined using func, when we run them, they will leave the address on the stack, which is exactly what we want. Here in my example, when I ran to 1K, K was defined using func, and it's leaving the address here on the stack. Okay, let me clear the stack. Okay. And the application operator we already saw it earlier. For syntactic sugar, I've defined also double parentheses, which is applying twice, and 3 parentheses, which apply 3 times. Okay, let's skip this one. So the I combinator is very straightforward. It's just we define it with the colon func I, and then we do nothing, and we end the word. So that's it. It's just going to return an XT of an empty word. The K combinator is a little bit more complex because, well, it needs to, we need to, well, I'm not going to enter too much in the detail because I don't want to spend the time on this. But what K does when we apply it is create another word. So we've got, again, enter, compile, and then there's a bunch of compile here, some stack operation to get the argument that was on the stack, the X, and store it into the definition. So it's creating here, I call it KX word, and this KX word encloses X. And when we will apply it, it will drop Y and put X back. So it's a closure, really. And there is the definition of the S combinator, which does this kind of manipulation twice. So if we look at it, when we apply S, it creates a new word, SX, which encloses X. And then when we apply SX, it creates a new word, SXY, which encloses Y and X. And when we apply this one for a third time, that's when all the X, Y, and Z are executing this. So this one was the trickier to get to. I've got a slide at the end that explain how I came to this definition, and it took a few tries before it worked really. But once we've got that, it's quite easy to define new combinators because, for example, if I do IK and I apply that, it's going to create a new word that encloses I, and simply I can take this xt and name it ki. So let's have a look at that. If I do, for example, yes, so let me clear the stack. I've got nothing. I do I. Let's have a look. So if we've got the xt of I, k. We've got the xt of I and k. I apply that, and now I've got a new xt. And this new xt, I can call it constant ki. So if you remember, so I should have nothing on the stack. Yeah. If I put a y, I put an x, and then I run ki, I've got my y, my x, ki. I can apply it. I can apply it again, and I've got y, and that's the definition of ki. Apply to x, apply to y, returns y. So it works. So that's quite that sounds quite powerful now. And well, for now, in this computational system, we've only got our three basic combinators, plus we've got the ki combinator. And let's have a look at defining booleans, for example. Before defining booleans, I'm going to define a couple of functions, .t and .f. So let's have a look at .t. So the definition is very straightforward. .t will just print true when applied, and .f, when we apply it, it will print false. And this dot parenthesis is how it's like dot quotes in other force, but in AlexForce it's dot parenthesis. So let's have a look. For example, I put, let me clear the stack, .t. So it's a function. So when I apply it, it says true. Okay. .f, I apply it, it says false. Okay. So far there's nothing. There are just functions. These are not combinator because they don't take an argument and they don't return a function. And I've created this bool word which will leave .f and .t on the stack, just so it's going to be easier later. So let's have a look now at defining true and false. Well, it turns out that true we'll say that true is k and false is ki. I think I've already got this definition. So if I say bool, it's leaving .f and .t, and I say t, and I apply it 3 times. Yeah, it says true. Okay. Here the thing is, what's happening? So we've left 2 functions, .f and .t, on the stack, and we apply k, which is true. We apply it, and it's going to select the first argument because it was k. And when we apply it at the end, it returns true. That's what we're seeing here. If I do the same thing with false, and I apply it, it says false. So it has selected the second argument because it was ki. And I don't know if you start to see here that it's really similar to the unary operator on other languages that we say if something, then the first, else the second. Well, that's exactly how it works here. So with that, we can start to create new combinators. For example, the not combinator, it takes a Boolean, for example, true or false, and when we apply it, it will select the first or the second. So now the definition, they start to become really big because we only have S, K, and I. So this is the definition of the not combinator, or at least it's one of one definition. It might not be the most the smallest one, but that's one definition. And when we write in fourth, that would be this one. So I can do that. I will do that. Let me select it. Select. So if I wait more. Okay. I'm going to select this text. I'm not going to type it. So let's have a look. So I'm going to write all this, and it should return false. So what is happening? I put my two fake booleans on the stack. Then I put true. I will put not, and I will apply everything. So it will apply not to true. It will apply all these sequentially to true, and then it will apply that to false and true, and it should return false. Let's have a look. And yeah, it works. And well, we can do the other test. It should work as well. Yeah, it works. If we look at everything, so we've got not is really the when I put all this onto the stack and apply it, it left me with just one xt, one address of a word that has been created at its time into the dictionary using the definition of ASK and I that we saw before. And then when I say bool, it leads to functions. I say f, it leaves me the xt of f, not another xt. Yep, and then we apply everything. And that when it's unrolling all the definition and executing everything, and it ends with the execution of the .t word. Okay, so I've got the definition of the and, or, NAND. It starts to become quite crazy. And XOR. So XOR is quite interesting because really, at this point, at the moment, we only have combinators that represent functions. We've defined booleans, and with this definition, we are able to test for equality. So that's quite powerful. And the equality of applied to two boolean returns a boolean also. And well, I think at this time, I won't go into the rest of because in the rest of the presentation, I've got how we can start to define numerals. So 0, 1, 2, and then add them, multiply them, and this kind of thing. But I don't think I will have time to cover this. So I think I would go quickly to okay, so that's the process and some references. Yeah, in this I will publish the slide deck later. Some references. I've inspired myself in a paper that I found that was about implementing SKI combinator in Forth. From this paper, I took the idea of the application the application word, but I didn't the whole implementation after that is original from myself, because I didn't really understand how they did it. So, but I took the idea of delaying application and executing using the parenthesis word. And I will leave also these links about lambda calculus, a couple of presentations that are quite interesting, and some information about the combinator, some lectures from Stanford that are quite interesting.
Mm-hmm.
Well, that's it. I don't know if you have any question.
Great.
I think that's
Thank you very much.
That was quite theoretical, not really practical. I don't think anyone is going to use really SKI calculus in any application, but
yeah. But we're looking.
I think the mechanism of the delaying application and all the closures and things, it was interesting.
Yeah,
to
we're looking
for me to
forward
develop.
for a second part, a continuation, maybe some other months.
Yeah, maybe.
Because the numerals are interesting, and there was also some question in the chat.
Okay.
By
Yeah, I
myself
didn't look
and
at the chat,
also
so
Atle.
ask any question that you have.
I can repeat them. So my question would be how you do memory management, because you create these new functions, and
Yeah.
is the memory eventually reclaimed, so it could be reused, or
No. So
so
that's
it's just allocated? Yeah, well, that's
yeah,
fine.
so it's growing and growing and growing, and I never disallocate it. There's no memory management at all. So
Yeah,
yeah, so that's
right.
of course that would be a challenge, and I don't know how to address that. So
And I think Atle raised the question: how do you do loops?
okay, so that's an interesting thing. At the moment, we've just seen booleans and up to equality. So I've not done loop. In lambda calculus, there is a way to do something. I think that would address this question, which is doing recursion. And recursion is done with something they call the Y combinator. It's got a definition, but I didn't manage to implement it. So the problem is when you execute it, it never ends. So it crashes.
Yeah.
So there's a way supposedly, and in the theory you can do it because in theory everything works. But when you start to implement it, at least when I started to implement it, I didn't manage to do it. There must be a trick that needs to be implemented. Yeah.
I think reduction order is important. So what parts you do first, and
Exactly,
if you choose the wrong part, you get into infinite recursions.
Yeah.
Right.
Yeah, there's something about lazy, and I don't know the term.
Yeah, exactly.
Lazy, not lazy loading, lazy application or something like this. So there've been a lot of study, I think, about this because it's the basis of the functional programming. So of course it can be done, but maybe I won't be able to do it in AlexPorth. I don't know.
The first part of the recursion could be the stopping condition, right?
Yeah, I don't know. Maybe.
Right.
That's a good question.
So that's obviously something for the continuation, and I'm looking forward to see the progress that you made there, and also the parts that you skipped here. So
okay,
maybe it's a good idea to just split it into parts, and then we see how things evolve. Thank you very much.
How do I unshare my screen? No, I'll stop sharing.
There's some red.
Yeah.
Stop sharing also.
Thank you, everyone.
I think our next speaker is Leonard. I think I saw you on the call.
Yeah, I'll do a presentation of Aegon Ford. I'll share the single window, and that's the that one.
Yep, I can see that.
And now I have to visit that window myself so I can start off. Now, this is what you see when you start up Aegon. This is the emulator, not a real machine, but the real machine behaves mostly the same. We do this one, well, most people put basic in their autoexec.txt. We could put Ford in it as well. But now we leave basic. We load Ford24 Ford24.bin, run it, and off we go. We're into Ford. And this is 24-bit Ford. The video game will as well run in the 16-bit Ford. The good thing is it will Aegon has a class of programs that are allowed only 32 kilobytes. And when you use that, you can just start them as a command like this. If we leave Ford again, if we do cf we have also a Ford, but it started as a command. From basic, you can start that from basic as well. But here the SP, the stack pointer is only 32K. But it's possible to turnkey the game, to turn the game in, to use, this is Spacer is the name of the game. We started here. Oh, and that's the demo effect. We can shoot the monsters, the alien ships. Not dwell on it too long because it's but that's how the game can be started as, and then it's a 16-bit, a full 16-bit Ford. Now back to the 24-bit Ford again, run, and now we see that we have like 400 kilobytes or so at our disposal, more than and but now we the video game, we will do spacer.fort, that will compile it. It will work on the 24, both on the 24 and on the 16-bit Ford, but on the 24-bit Ford we have some goodies like view. We can look at words now. We can view spacer, for instance, and boom, we are in the editor, and we have the instruction screen here. Quite old school, the instruction screen. But the main loop is the most interesting thing of the game, I think. We start out with the V wait, that's waiting for the vertical retrace interrupt. It's the, you wait for new frame, so that's your time base basically. Then we're checking a lot of keys, like the key 1 key code. If we set the lift values, if you press one of the digit keys 1, 2, 3, your rate of ascent or descent will be adapted. If we press the cursor up, we do the lift, fetch the lift variable, negate it, and add it to the, or put a negative rate y, a negative, so it go 0 is top row of the screen, 31 is bottom row of the screen. So if we have the key down, we put the lift value and and then don't negate it. So we go to the bottom row, towards the bottom row. Then we have the set rate X for those are fixed values, -8 or +8 for left and right. Space is firing the laser, that's our fire button. Escape is quitting. The number of ships is reduced to 0, so the game is over instantly. Those are the keys. And what the Aegon operating system in fact does is the operating system, when a key interrupt comes, it will, apart from providing the ASCII value of the key actually pressed, it will, depending on if it's a key up event or a key down event, it will set a flag in a bitmap. So we can at all times just check that flag. Is the cursor down key pressed or not, or is the cursor left key pressed or not? Aegon provides that service, so we use it. Now, that's the doing the key stuff. If the laser temperature we let it cool down if the laser isn't pressed, the fire button isn't pressed, we let it cool down gradually. If it is pressed, it will go up and it will eventually overheat. Then what's good to know, it's an what you call it, it's a character-based, we used character-based graphics. There are two reasons, in fact. First, I found it simpler just to implement it, to get a hang of the video game logic. And second, there's another computer that's called Cerberus that actually only has character-based graphics, and I wanted to keep the door open to port it to that machine as well. And probably the Aegon version will gain sprites and pixel scrolling in the end, but it's not here. We scroll the whole background to the left. This is the scroll timer thing. The scroll period so once in every 4 or 8 frames, we scroll the whole screen, the whole background, one character to the left. Scroll background function. We have another timer that we increase, and then if the timer reaches the end period, we add an alien, an enemy. An enemy can be one of the ships we just saw. Then there in the main loop we reduce the fuel level. So if the fuel is too low, if it reaches 0, we force the Y rate to 2. So we force the ship to descend, so to crash into the ground, in fact. And then we show the score if the fuel gets to a certain low point, when it changes to the next tick on the fuel gauge. Move ships does the logic of moving the coordinates of the ships by their rates, and then redrawing them again. We had a hide ships, and then there's a collision detect. If we are collision detect, we quit the main loop. We remove one of our ships from what we have. We top up the fuel, set fuel tops up the fuel of that new ship we have, and then we repeat. That's how the main loop works. We could refactor it into much smaller details. Let's see what, say, the scroll background thing. That's, I think, the most interesting part of that game. Now, first, this is a self-contained game. It has all the custom graphics as 8x8 cells. I can basically design them in my head as hex numbers. I used to work on a TI-99 4A in the 80s. That was the way hex numbers was the way to go to define your characters. So we have some defining words for them, some words to define these characters. The ships, the exploding ship, etc. The background characters. Now, these are as an array of strings, a stupid array of strings, if I would say, a list of strings terminated by a 0-length string, counted strings, that defines our background. Then That's what's shown on the bottom, the yellow thing you saw earlier. And we have another background that is for when there's a tunnel. And you see there's this fuel thing. That's where you have to go to refuel when your fuel is low. And that's, then there's another thing that's the background pointer that tells you what string to pick from the background. There's a scroll sequence. Now, that's a video sequence. Aegon doesn't have a memory mapped screen. It uses the ESP32 to generate video for it. The ESP32 has a big set of commands like patterned after the BBC basic video commands. So cursor up, cursor down, draw a character, draw a line, plot a circle, anything like this, but also to set a window, to scroll text. And this sequence first set a text viewport to exclude the bottom row, so the row with the score will not scroll, just what's above it, like it's doing up and including row 27. Then we actually scroll by 8 pixels to the left, and then we undo the text window again. That's the scroll sequence. Now we are now we want to go to the scroll background. What the scroll background does is it does the scroll sequence here. That's it's instructing the video processor to do that. So we don't have to move the bytes around ourselves. Now we have the play field. The play field represents the characters that are in the background. These are the little white dots that are the stars, and that is the yellow background. And the asteroids when we have asteroids. And then we do a row by row. We step through the play field array. We move the characters one to the left, a 32-byte C move. We move the rows of characters one position to the left. Then we use the new char function, the new character function, to get a new character in the rightmost position in that row. And the new character function is kind of complex, more complex than it should be. We store it in the play field I plus 39 plus C store. We store it in the play field array. And the play field is used to redraw characters that we override with our ships or with our laser beam, and it's used to detect collisions. Then we emit that character as well at its XY position, the row number and position 39. That's the rightmost position in that row. We draw the new character, the same new character. Then if we are at a certain row, we switch the color from white to yellow. So the the lower part of the background will be drawn in yellow. And we step by 40 plus loop. So we step through the playfield in steps of 40, and each row is 40 characters. So that's the first thing. And then we have we put the background pointer, we move it to the next string in that list that you saw. And if we are at the end, if the fuel is low, we just set it to the start of the fuel tunnel list, and otherwise we use the normal list. And then we update the background pointer. And then the new character function, definitely up for refactorization. But what it does is, if it's if the row number is higher than a certain value, we just take the byte from that row, and otherwise we draw something on the screen. If we are in asteroids mode, this is all logic of drawing. An asteroid consists of 4 quarter circle parts, and we draw their completion. If the enemy mode equals 3, we will ever start a particle, an asteroid, draw a new random asteroid, and if not, we will, and there are several conditions under which it's too complex for it to explain here. But well, when we didn't have asteroids, it was just randomly picking either a blank or a dot for a star. So what could we do now? We could do a little playing with the game. We want to see if we can enter the fuel tunnel, and we will set fuel, get there, and instead of 10,000, we give us only 1200. Then we have frequent refueling, and then we save and we do OK. Is reload the currently selected file, and oh, that was a bummer. That's the demo effect. But we have far less fuel than we should have normally. Oh, bummer. I'll play better when it's not demonstrating, but we shoot the lift. Now we are in the fuel tunnel and we see the fuel going up. But, oh, now our laser overheats. That's also in the game. What you see, I'll play once more. Oh no, wrong one. And now we, this is. Now we have the, oh, now we crashed into the ground. Oh, this is pathetic. But if you don't refuel, you will be treated with a forced landing like this. So you have to refuel. But it's now that's the one thing you won't add it again. We can view set fuel. Oh, how much time do we have? We can do it at normal. We can show you the asteroid level. I think I can. We have it now in the normal. Did we? Don't guess. Set fuel. Did we change it to the correct? Oh. No. That's. Oh. Now we there. Yeah, 10,000. That was the right number. I don't have to save it now because it was already there. Okay. And there are nice things like there's some hidden. So these are ships that emit missiles. The missiles that are on these things are also governed by the move ships. These are our own ship, the enemy ship. Now these are the asteroids. These are part of the background. You can't blast them away with your laser. You have to dodge them. But I think that's enough now.
That's great, Leonard.
Yeah, and then of course there are nice things like when you are at a higher level, you get less fuel. When you get a new ship or refuel, and when you are at a higher level, you have to hit each enemy ship twice or 3 times before it dies, and it changes color in the meantime. And I got all that logic implemented in Ford. Are there questions?
Yeah. So I don't know whether anybody's got any questions. I've got a question. Your code seemed quite readable. That was good. I did wonder the scroll routine you were showing. I think I'd have found that a bit big to debug. How did you? I mean, I'd have probably split it up into like maybe 3 or 4 words and test them individually. How did you actually debug that function? It looked quite impressive.
Of course, not everything was in there when I first wrote it. So things got added to it. And of course, there are things like the new character function that were split out. And but indeed, even debugging the scroll sequence itself, like how to set that text window and command the VDP to scroll, it has some trial and error. But you can have, it's not ideal to debug an actual video game. You can, in some cases, you can inspect variables, you can run a function by itself and see if the values are what is expected. But sometimes you see the ships wandering off to the wrong side of the screen and things like that. and you're scratching your head. You get some. So it wasn't all of the functionality wasn't written in one day, in one go.
Yeah, so some of those functions, I mean, you can easily see the main loop, for instance. I
Yeah.
mean, maybe it's always with code, I guess, there's refactoring, and you can,
Yeah.
you know, I think that's a fourth motto that's applicable for everybody, but you know, but the main, you can see that you added piecemeal. I think that it's sort of interested as well on, yeah, I mean, you've always got the problem. I think everybody, whether you're using communication systems and communicating between multiple micros, whether you're debugging a video game, sometimes you can run individual words, but sometimes it's interactive and the failure modes are interactive. So
and I think we did a lot, and one of the things I want to port this to Cerberus, and it has an actual character screen. I do have something running on that one, but it's I need to I reorganized the logic a bit. Otherwise, when you're just printing the characters like I did on Aegon, it flickers like hell. It's completely unusable. But it's still, Aegon is, say, almost an order of magnitude faster than Cerberus for the fourth interpreter. So you are going to, like the random function is using 2 multiplies. How can we reduce that? How can we shave something off that? So we have to optimize something and maybe use some assembler assists to make the game interesting under Cerberus. But now, if there are no challenges, there would be no fun, right? Can we stop sharing now?
Yeah. Thank you very much for your talk.
Clear the floor for the next speaker.
Thank you very much.
Thank you.
Thank you.
Yes, the next speaker is going to be Pablo Reda, who's going to talk about Forth and OpenGL without floating point. Pablo, have at it.
Hi, thank you, Ulrich. I share my screen. Okay. This is my odyssey about using OpenGL without floating point. OpenGL is a standard of GPU programming. Is a API for rasterizing triangles in 3D, have a near many system scale. All of internal number are floating point, and this is OpenGL. This is now all the future is Vulkan, but it's much more complicated. I try to using OpenGL in my version of 4 called for R3. R3 not have floating point by design. The actual version connect with any dynamic link library, but only with integer parameter. Floating point parameter is a mess. In early OpenGL API calls, you need a floating point parameter, but new API call not. I think because it's much more efficient copy the memory from CPU to GPU in block and not parameter but parameter, and then the new function prefer a copy chunk of memory, and for me this a good news. And then I try to make OpenGL programs. I show how different how different version of R3 manage control the IO with the operating system. Previous R3 incarnation have in the virtual machine the words for making, for example, graphics. Then this is the main dictionary of R3, and this is the word, the tokenizer in C. And when, for example, I make graphics, I need to define the word for make graphics, and in the virtual machine need to call the access to this function. For example, here, making lines and set the graphics, or playing song, and then I have a problem when I try to make a new capability to R3. I need to modify the interpreter. R3 can be compiled too, and the compiler is in R3 too, and the compiler have the same problem. I need codify the routine, the code for make lines or graphic or whatever, and net call to function to make this. But in seeing the UA4, I think the Brad Nelson UA4, this is a PC version of SP32 Brad Nelson used for this PC4 a very good idea is make only word for load dynamic library and call for and call this this function with a fixed quantity of parameters, and with this type of connection only need this word for make this load a library, get the address of the library, and make the call with 0, 1, 2, 3 parameters, and then with this I make all the connection with any DLL. This is again, this is the word of R3, and this is the word for IO communication. This all. When I compile R3, this is a little more complicated. This is the call for example, 4 parameters, but only need this word for any dynamic line library. Well, how work? For example, in the R3 communication with SLD library, SLD library is a library for make graphics multi-platform. Do this for this connection. Load the library, and with the address of the library, I get one by one the function I need, get the address of the function and store in a variable, in a local variable, and then make a word for call this address with the correct number of parameters, and then now I have access to the, in this case, SDL library without modify the interpreter or the compiler, and this is a big advantage. Then with this, I have access to this library. Well, then here the previous version call to API wire in interpreter and compiler. I say previous of this, and now with the idea of UF4 from Brad Nelson, I make this modify and now call any DLA. Then I start to learn, or I try to connect to OpenGL when I release this change in the use of floating point parameters. I don't have this capability. Well, then I make I found first when I start, I very confused with library with like Leu or GLF, while I don't understand why this library what doing with library. And then I found like local library and GL get prog address that this function make the same I do with the DLL library. Then when I have access to these two functions, I can make the same with to get access to OpenGL library. Then I do the connection with OpenGL and start to make access to these functions here. Then when I use the OpenGL, I call this library with include and access to every word who I make the link. One piece, I need one more piece for make this work is transform fixed point to floating point. Big reg scale here in this meeting show a similar problem in previous meeting. I have a fixed point numbers and need the representation in memory of this number in a floating point. Only the representation in memory, not necessary operate with this memory, because I need for transfer this number to the GPU. And then with this word to transform fixed point and to floating point or floating point to fixed point, I can fill the buffer to OpenGL and send to GPU to work. These two words for make this are here, fixed point to floating point. The only strange thing is I need a shift with signal with negative need a shift right, and positive a left right. And this is the work for in R3 to transform a fixed point in floating point and have the inverse to floating point to fixed point. In this case is for example real format file from object, 3D object or animation or whatever, and need to convert to fixed point for work in the R3, in the fourth R3. And I have another word for integer to floating point, but it's not very useful. Well, with this and the connection, I make this simple example. Is like hello world for 3D graphics. Is make a triangle shaded, and I need use only a function call with integer parameters, and then I not have to use a function from floating point parameters, and only have a use function with address to chunk of memory with the floating point parameter. For example, here I make three chunk of memory called B0, 1, and 2. Here I make a 32-bit every word and convert every fixed point number in a floating point representation exactly here. Fill the vectors, take this memory and convert to floating point, and use this call to OpenGL and pass the address of the vertex for make this triangle. Well, this is working. I'm very happy to see here when I release it and start working to advance in the OpenGL. For still OpenGL, the best place is this layer OpenGL. I do with this web page make every demo here, and of course need to transform the C code for R3, and first make a cube, rotated cube with texture, then make a load an object. All these graphics I do in previous version, but all in CPU. And for example, the load of file format I already have. I advance in more example. Here I start with multiple objects. I try different capabilities. Every of this source code have more and more complication. For example, the recent, you need a constant, you need a load, a shader, a fragment shader, and a vertex shader. You need a pass parameters all in in floating point to the fragment shaders. You need, for example, make a camera. Here I fill the buffer with vertex, normal, UV, and an index. I call to draw this object here. An interesting question is about need a matrix calculation, and I have a matrix calculation of all code. For example, this is a matrix with all fixed point, and I have a matrix calculate perspective matrix or orthographic if you like. I need calculate the matrix for camera and multiplication and rotation and inverse matrix and so on, all in this case, and only need transform to floating point only when I send to the GPU. But prior to send, I have all in fixed point. For example, in this web page, this is a shadow mapping example with the explanation how do shadow mapping in C, and this is, for example, this is my version of the shadow mapping, with camera moving. And this is the same example, only with the connection with SDL library. And I make a bitmap text. I make a more complex text called multi-signal distance field text with I can change very easy the size of the text. And the last demo is my goal is make a simple library in 4R3 for make 3D games. And this is a start to make a third-person example with terrain movement. And have another example is a load a format library. I have another more pretty. This is load a format file of 3D characters. I don't I have problem with the bone animation with this character. I not finish them. Perhaps someday I can make this. This is how work ugly. And this is an example. The last demo is I like to show you. This is a full demo, and try to convert this to platform to write 3D games with exporting characters and then. Well, this is all. Thank you. Any question?
Wow, great.
Impressive.
Very nice.
3D
Impressive.
graphics high-end graphics driven from Forth.
Yeah.
Wow.
So,
That is cool.
Are there
Is the
any
code
questions?
online, Pablo?
How again?
Is the code, is the source code online? Is it on
Yes,
GitHub?
yes. Download the code, and this is whole here. It's window only. I am searching for a Linux guide to make the part
Port. Yeah.
for make R3
Yeah.
multi-platform. The previous version, the version I show you, with need modify the virtual machine for call the API. This is multi-platform: Windows, Linux, Raspberry, and Mac. But I don't make the Mac and Linux version. Some guy helped me, but I waiting for make this version multi-platform. I prefer programming for, and I don't like to program C to make the connection and then make this.
Excellent. Are there any further questions? That's not the
Yes,
case.
Christian
Yeah,
has a question.
Christian. Yeah, sure.
Hello, Christian.
Hello, Christian.
I watched this and I'm impressed, but I still wonder, how did you get OpenGL usable within Forth? How did you integrate this? Did you rewrite the whole thing in Forth?
Yes. Only need the connection with the driver, the VC driver for the GPU, for the
But this has always been a puzzle for me. How do people go from Forth to a library that is in another language? OpenGL is in C or whatever.
Yeah, you need a load a library with OpenGL capability and use the same function I use.
But you created them all in Forth.
Yes. Only have the address of the function in the VC driver. Is the only.
So OpenGL was only used as a model, and you implemented that model in Forth.
Yes.
That's impressive.
Yes.
I have to read what was OpenGL. I didn't even know what it was. So thanks.
No, Christian, to answer your question, I think I have a clearer answer to this. What you're looking for, Christian, is to look what is called a calling convention. On a given operating system, libraries always have very definite calling conventions. So as long as you in your assembly code, which we've seen the code that Pablo showed us with the sys0 and sys1 and sys2, this was Windows calling convention, and it was implemented in assembler. And this is all you need to do to call onto a library that can be in any language. So when you're going to look on Wikipedia or something, you look for calling convention, and you'll learn about that. So this is what Pablo was doing.
Okay,
Thank you,
so he
Virgil.
used calling conventions to call something that was within Windows. Okay.
Yes, this code was Windows
Essentially-
specific. So when he was saying that he was looking for a Linux guy, this is because you need to know what Linux calling convention is, and if you want to run a NetBSD, it's going to be another calling convention and stuff like that.
Essentially, Christian, the driver doesn't know what language is calling it. It has no idea.
Yeah.
It all looks the same.
Yeah, they're often called FFIs, or foreign function interfaces. So some Forths have those foreign function interfaces built in, but even for other programming languages like Python, there are foreign function interfaces. You can load a DLL, for instance. I think there is some support in, for instance, GForth SP Forth, I think, has also got this foreign function
Exactly.
interface. Some of them are better than others. So some of them are very low level, and you can load a DLL, a library, and you have to manually. I think that's what's being done here. You have to identify every single. But there are some that have got higher level interfaces where it can analyze, for instance, if they supply a C header. And I've seen Forth code that parses those C headers and produces the Forth equivalent of that. So that makes it a little bit easier to integrate. And in fact, there are builders for this. I think is it Swig is one of them?
Yeah, Swig.
To build a target language from an interface specification.
Yeah. So we've been talking about our schedule going from monthly to bi-weekly, and maybe it's good to have workshops in these cafes and a closer look at some of these topics. So my proposal here right now would be having some kind of foreign function interface DLL calling workshop in March. No talks, but just hands-on and have a look at how this works. And we pick a system and we can demonstrate how you invoke library functions. I think that's a good idea.
Okay, second question for Pablo.
Yes.
I also have the impression that you had a challenge adapting Fort and OpenGL because you didn't have floating point. Is that, and you had to make fixed point look like floating so that you could use the OpenGL. Because I heard you talking about conversion between fixed point and floating point. Why did you have to do this? Was it because you didn't have floating point?
Yes. The question is the OpenGL prefer now a chunk of memory with floating point inside. Then I don't need have the floating point number. Only I need have the memory with floating point number. Then I can convert fixed point or integer in this floating point representation and store in memory and send to GPU. And I see the opportunity to make this without have floating point. I don't have floating point in my system. I hate floating point for simplify.
You found a way around it.
With floating point, we have a lot of problem. We have the problem of precision, of comparison, and you have variable resolution. I prefer fixed point. And this, I see this opportunity and work very well. I don't see Vulkan too much, but I guess Vulkan don't have a function with floating point parameters.
I think for your next presentation, Pablo, I'd like to know how you did that simple little part there. Make fixed point look like floating point.
Well, Bill Rex explained very well in a previous meeting. He need convert a different format of floating point and make this transformation. I need a transform fixed point and floating point, and this is the two tiny words. But need the knowledge for make this, and it's not very common, but exists.
Well, thanks a lot, Pablo.
Well done. Well done.
You're welcome.
Thank you very much. So we proceed in our schedule, and our next speaker is Cornelius, and he will be talking about a simulator that we found somewhere by Swedish guys, but Cornelius will introduce this. And we did some common work, and he will give a sneak preview of what the NC4000 Novix simulator looks like. So, Cornelius.
Party time. Yes, we go from high-end graphics to no graphics at all. So if you ever wanted a paradigm shift without a clutch, here it is. Let's take a look at the simulator. Screen sharing, would you please share? Here we share.
Yeah, well,
okay.
black screen with green prompt.
Indeed. Hey, the 80s called. They want their terminal colors back. Is this readable for everybody?
Good for me.
Okay.
Yes.
Cool. Good. Novix simulator.
Too small. Too small.
Say again?
Too small.
Too small. Okay, we can fix this. Just give me a moment. Change settings. Appearance. Change 18. Let's see what that does. How's this?
Good. Good. Now good.
Perfect. Okay. We'll go with this. Good. Yeah, Novix simulator was written in the late 90s at Chalmers University in Sweden. It's part of a thesis about an MP3 decoder in FPGA. The FPGA was implemented a Novix CPU, which at that point in time had been out of production for a decade. So to get an idea how the code was supposed to work, to write code, to debug code, they came up with a simulator. The simulator is mainly written in C++, fairly compact, consists of a couple module, the core itself, implemented as NC4K, then the environment simulation, which basically handles I/O, has a couple of general, this thing in general is just minimal memory management. And then we have the bench, aptly named, that's the main program, which offers, well, which brings up the whole thing, gets it going, allocates memory, and offers you a very, very basic, well, today we would call that hypervisor, something that controls a guest CPU, allows certain interaction with this guest CPU. The code itself compiles just fine on 32-bit Linux. As I found out last night, when you go to something newer, 64-bit, there are a couple of warnings, and there are some adaptations that you have to do to some of the built-in types of this thing because they've been used elsewhere. The code itself, the baseline code, dates back to the late 90s. It was written in Borland C++, which I'm pretty sure itself is long dead. There is a successor company, Embarcadero or something like that, where you can still get licenses for that stuff, but it's Windows only, so why would we be interested? Building this is quite simple. There's a make file for this. You're on a make all. The platform we are running this on is a Pi 2B. So 4 CPUs at 900 megahertz a pop. which means once we start that thing, we won't quite die. If we want to start this, we just invoke this, NC4K. It throws out a ton of text. What this thing now does is it loads from disk the firmware. The firmware used to, on the real thing, the firmware sits in 2 EPROMs, which are copied to RAM at part of startup. Well, we don't have a board, so the firmware is loaded from disk, from images that I retrieved from the original ROMs, EPROMs twice. Very first thing I did, because EPROM's life expectancy is not exactly in the 35-year range. When we come up, we end up in the hypervisor, which means we have a couple of very, very basic commands. We can display memory, and since forth has 3 different address spaces, and these 3 different address spaces, return stack, data stack, and main memory, are distinct on the CPU. There are 3 different commands to manipulate or look at these. We can take a look at the CPU registers, which, since this thing hasn't done anything, are very, very empty. Of interest here is the program counter. An NC4K starts out when booted at address 1000 hex, so 4096 hex. Rest is empty. Pointers are reset. You can, since this is a simulator, due to the nature, the way this is coded, you can run this thing single-stepped, which with the original board you couldn't exactly do unless you were into really hefty hardware modification. Hardware modification, in our case, is not an option because there are only 2 known boards in existence, so we shall not mess with it. At some later point in time, I'm thinking about putting this on a microcontroller and see where we go with this. Anyway, we can run this thing. We say go, and it waits for a moment. And since this copyright notice doesn't look completely English, that's a hint right there that we are running with the German version of the firmware. We can do a words. Oh, lovely. Caps lock, please. You can do a words, and it spits this out. Now, if you got the impression that output speed was kind of not so fast, then you're not exactly mistaken. There are 2 versions of this emulator. Ulrich's does I/O way faster than this, because his version intercepts calls to emit and key, so the routines which display 1 character and which receive from the quote serial port unquote 1 character. His emulator intercepts calls to these 2 functions and switches immediately to native, to what this basically takes the character that's supposed to be sent and shoves it immediately into the appropriate file descriptor. Mine doesn't do that. The Novik CPU, BitBingo's a serial port with software timing. My version bit bingos a no longer existent serial port with all the timing, and therefore this bit bingo takes longer. What else does this thing have? There is, since this is an emulator, there is a little bit of a timing penalty, but it does the basics just fine. It has a load command, and it does not have any disk access from in here. I want to be out of here. I need to, start me a virtual terminal. We shall use screen because that has been around forever and works everywhere. So let's start the simulator again. We have the simulator. Does a ton of output because the emulation environment iterates the fourth dictionary pointer chain to find out which routine resides at which address. Just a gimmick to see if I loaded my code correctly. Switch to a different screen. Let's see if we have any source code on here. Let's try this. Yes, we do. Remember, back in the old days, fourth mass storage, persistent storage access was done in blocks. A block is 1024 bytes of typical text data, 16 lines at 64 characters each, no carriage return. Each line had a fixed length of 64 spaces. And, well, that's how source code got read in. There were commands to load and store blocks directly from disk. And we demonstrated last time around the capability of the real CPU together with a homegrown terminal program to store, to save and load blocks over a serial port. That's called the serial disk protocol, and that was the native way of a Novix to get any code loaded. Now 1024 bytes, doing that in a text editor gets a little fumbly. So the simulator also supports a fourth file format, which is basically, we take a look at one of these, which is basically a text file. You can load that into any editor of your choice. And load this into any editor of your choice, VI or whatever. You can edit this. These are regular lines. And the runtime environment pads this out to 64 characters per line. So please don't make them any longer. And please do not have more than 16 lines in your fourth file. We can load one of these. No, we need to start the simulator first. Dum-de-dum-de-dum, there we are. Shall we remember caps lock? We do an 8 load. And that takes a moment, and we come back with OK. And yes, the delay, the noticeable delay between hitting enter and the OK comes courtesy of my big bit bingo exercise. If we now do a words, we have something that scrolls out way too fast. Let's go back and display what we just rolled out of the screen. And that got cut off. Lovely. Do an 8. Load again, do a words. And somewhere here they have to be, I want this in hex. Words, okay, here we go. They need to be at a, there they are. My 2 words have been compiled to addresses 9A and 8A, and they are there more than once because I loaded this thing more than once. What these do, this was one of the problems that we're faced with, that the emulator, an emulator, chances are the timing doesn't match the original, and we shall see in a moment how badly that is the case. The emulator has a timing issue, inasmuch it started feeding blocks way too quickly to the simulated CPU. The simulated CPU was not ready for any kind to accept bits, and this thing started throwing in bytes fast. So I thought, okay, fine, I just load the same functions again, again, again. Run a load command, Eversoft, repeatedly. To my great surprise, one should read source code and documentation before one embarks on these kind of exercises, which of course I didn't. That would have made sense. Forth remembers, or the CM forth remembers which blocks it had loaded. Has 2 buffers. One at hex 800, the other one at hex C00. If a block is already in memory, it will not load it again. I was under the impression that I'm reloading. I was not. As a consequence, the load command didn't really load. So the serial port got never exercised. If you think about it, doing things this way makes a lot of sense, because serial ports at 9.6 kilobit are not exactly the fastest thing on the planet. And yes, we are talking 9.6 because this was the late 80s and 115 wasn't really an option. So we came up with these, or I came up with these 2 caps lock again. Functions send block requests a block from the controlling terminal back in the old days, from the device that was talking to the board, but hey, we no longer have a board. It's all virtual. So let's use virtual machine terminology. You have a host, you have a guest. The Novix is the guest. The hypervisor on the real hardware is the host. What this thing does is send block requests a block, read block takes a block from disk and, well, reads the block. So what else is in here? Everything else works pretty much as it used to. Where is the test routine? Where is the test routine? Like there's self-test code for memory. I just have to find, here we go. Let's run this thing. And it does something. What else is there? Yes, it's an emulator. It's an emulator. So one thing you don't have is hardware. So the old board had all its pins on an edge connector. You could basically go out and attach TTL level hardware, 5 volt, 0 volt stuff, fairly straightforward, fairly easy to do, and start talking to it. That doesn't exactly fly these days because this is a Linux box. Well, in this case, it would fly a little bit because this is a Pi. A Pi has GPIO, so it would be possible to map some of the virtual processors, virtual bits to actual ports, and then start playing with 3.3 volt logic chips, modules, whatever floats your boat. So sorry, it's not 5 volt tolerant. You would have to do something about that. But there's one caveat. The original was clocked at close to 8 megahertz. That was as high as it went because memory chips back then, well, they topped out at that rate. You can probably get something faster right now, but 8 meg was as good as it got. The Novix executes most of its instructions in one clock cycle. Since you can piggyback more than one instruction into the same instruction word, a Novix is, there's no microcode. Every bit in a word, every command directly controls something in the CPU. There's no interpretive layer, whatever in there. A return instruction has its own bit. Therefore, a return can be piggybacked on other instructions. But for rule of thumb, a Novix can execute 8 million instructions per second, unless one of the only instructions, or there are instructions which require an operand, which would be a memory address. These take 2 instructions. So if we assume a mix of, say, just give me a number, 80-20, or yeah, 75-25, let's say 3/4 of all your instructions are single word instructions, then you still top out at 6 million instructions per second. This is a Pi 2B, 900 megahertz. So let's find out how many instructions per second this thing does. If we do a control closing brackets, the simulator has an instruction counter. Each instruction counts it 1 up. If you hit this thing just right, then it tells you how many instructions it did per second over the last measurement interval. This right now is 1.3 million instructions per second. Do that again, this number will drift a little bit, but it's going to be in the same ballpark. If you hit this too often, your precision tanks, but it will get back. So you're talking 1.3 million instructions per second. Spoiler alert. This is 900 megahertz. And remember, we are talking 80s tech. If we run a top, we can see a couple of interesting things. Like for starters, I've been talking about this thing, or I've been running this thing now for 10 minutes. The emulator, remember, there's little supporting hardware on there. And oh, by the way, it also doesn't do interrupts. The CPU interface is bit-banged. The serial interface to this thing is bit-banged. That means this thing pulls the whole time. There's no pause. There's no idle state in this emulator, just as there is no idle state in the real CPU this thing is always doing something. As a consequence, it will busy out one CPU. The only reason that we are getting these 1.3 million instructions out of this emulator is it has its own CPU. So if we look up here, our CPU utilization is 25% in user space, very little in system. We are 74% idle. If I were to crank up a second one of these, which we can do, not a problem, we would be looking at 50% CPU. So if you get any ideas to do this on something with not so hip temperature management, let's find out how we are doing. We're looking at 42 degrees centigrade. Before I started this talk, I checked I was running at 39. This is a Pi 2. A Pi 2 has a decent temperature budget. If you do that on a 4 or a 5, expect your fan to never go off again. What else is there? What else? Oh yeah, we need to talk firmware. The firmware of this thing is the original, it's the one from the fourth Systeme Angelica Flash, the German distributor of this board. There's also an original firmware that came with the simulator. They don't differ much. There is the different blurb for the copyright, and there was one instructions which changed the number for a times, how often times was executed. That came courtesy of an off by one bug that got fixed in between. But firmware, you can of course compile and load your own because hey, it's a simulator, it's easy. Firmware comes in two flavors. You can do either bin files, a binary, just a binary blob of length of 8K, because that was the original length of the EPROMs. Surprise, most of them is empty. This is very memory efficient. The other one are hex files. These hex files are a leftover of the EEPROM burner that I constructed from scratch for this thing because I didn't want to exactly entrust irreplaceable memory chips or firmware chips to some programmer device out of China, which even when it's more expensive still comes with questionable documentation and who knows what kind of drivers. So I built my own. These hex files, we take a look at them. They look very familiar because they are Motorola S records. It's pretty much what programmers, it's one of the formats these programmers understand. The other claim to fame of these things is that they are really easy to read, and a read and write mechanism for them is implementable without too much code. So, and this is pretty much as good as it gets. As far as sample code goes, the fourth files here, if we take a look at them, most of them are tiny. Number 6 is a little bit chunkier. This thing here demonstrates some of the issues that I've had with the simulator. I did not have, I needed a function that sets memory to test the disk I/O interface. And I had some issues with the simulator stack, and I wasn't quite sure how my stack looked like. Could look at it from the outside, but I wasn't quite sure if stack access the stuff that I expected it to access on the stack. So there is some stack manipulation here that would not make any sense for a real system. But if you would like to find out where on the stack something ends up as in comparison to real memory, if you maybe have an off by one in there or something like that, it helps if you can write certain patterns onto the stack and then look at them in the outside monitor to see if they ended up at the right address. Again, lots of debugging. There was time spent on this. It's not yet available because it's a little bit rough on the edges. And I would like to add a merge Ulrich's code, which does I/O way faster than mine, into this, so that you have a choice of what you would like to do. Let's see if we can at least make read block work on this thing. It requires a block and an address. Do we have any blocks here? Are there any BLK files? Yeah, there are BLK files. I have, for instance, one that's called BLK. This thing here, ooh, that looks like binary gobbledygook. It doesn't matter. Let's try it anyway. Our simulator is still running. We could state, what was the calling convention? Block number first. And we need an address. Are we in hex? We better be in hex. I don't want to overwrite my code, my firmware. Let's say we want to read block number 0 to address. This thing is 32 kilobytes, so let's start load it at the 16K boundary BLK. And it reads, and the suspense is killing me. And I think I just hung this thing. Oops. That is not a problem. We just boot this again. Quit out. Say go. Say go. Caps lock. Do a no. Hex. Do a 4000 read block. Why not? Oh, because I forgot to load that stuff. Take a look at this block again. So sends the block, puts 1023 up there, wants the number of the block first, then the address. Number of the block first and then the address. Let's do it the wrong way around. Yeah, now I really overwrote something. But we can stop this thing and now look at memory. Help gives help. We want to display memory. We want to display this, no, not uppercase, lowercase. Display this from address 0 for 100. What am I missing? Oh, I forgot to specify which memory. And there is my memory, and apparently I did not step on it. Well, okay. Future works. Anyway, this is that. Oh yeah, you can run more than one. Last but not least, let's busy out this thing. You can run more than one of these. And if we now look at top, there are 2 of them, and they're happily ticking, and they will happily eat your CPU. Again, on a newer system, which more intricate memory and CPU management, you probably can get to the original utilization of the original system. But don't expect any real-time performance out of this, especially if you cannot dedicate individual CPUs to the simulators. Perfect. That's that. Questions, please.
Thank you very much. Thanks, Cornelius. Are there any questions? Everyone's overwhelmed.
I get that a lot.
All
Yeah, I
right.
know. This is a little bit the sip from the fire hose. Just wait until we walk through the code.
Yeah. Anyway, well, we can do a scheduled break. Yeah, so that is what our current schedule says. We will have a short break, so everyone can sip coffee or tea or whatever your favorite beverage is. And my proposal is we will meet in 15 minutes. Is that okay?
Perfect.
Yeah,
Okay.
which is half past whatever your hour is. Okay.
Can you put a link to the emulator somewhere? I always want to play with the NC 2000 CPU.
NC 4000. The 2000 is the Harris that you're thinking about.
Okay, yeah, the Novix chip.
Yeah, yeah, I can put this, but keep in mind, this is work in progress.
Yeah.
This is work in progress. And so there is this thing is likely to change without much ado. Might put this on GitHub or wherever we put this stuff. I can probably put something. Yeah, I shove this onto my website. Give me a second.
I had some conversations with Dr. Ting, and I asked him about the Novix, and he had several boards unused, and he would sell me one for $150. And being foolish at the time when I had money, I didn't buy one.
Ouch.
And yeah, and now I regretted it a bunch because it sounds like an interesting device.
Yes, it is.
Hey, I tell you what, as far as Linux versions go, the majority in here, are you running a 32 or 64-bit Linux?
64-bit Linux.
64.
Okay. In that case, we'll do this different. I have another version, but on Ubuntu. Ubuntu LTS on Intel, which I'm currently getting to the point that it no longer complains. The compiler complains quite a bit when running on a newer Linux. This box has been on purpose not gotten anything but security patches. Because it's an outside-facing device. So if you had a VPN configuration, you could actually get in here and play with this thing. B, it's a 32-bitter and it's a little bit older.
Okay. Well,
if you take the code and put it onto a modern OS, then it's not going to compile. I have one that compiles, but it throws away too many warnings for my taste. So the way this is going to work is I can publish this one with the caveat that it will not build on a newer OS, but you could look at it. Or if you give me a couple days, then I can put a newer one on there and shove this into Facebook and the usual forums.
Okay.
Your pick.
Well, I have, besides my multitude of computers all running Linux, I have some Pi 2s, Pi 3s, and Pi 4s that are just sitting in a box being unused.
There you go.
So
there you go.
I could load it up on, like a Pi 2 or a Pi 3.
That would
And
work.
it wouldn't hurt my feelings at all if it's dedicated for that purpose.
Yeah. Again, be careful if you put this on something that does not that does not have enough anything with a temperature budget challenge will might take damage.
My Pi 4s have metal heat sinks.
Oh, good.
Connect to all the major chips and dual fans. And I'm on a hot day, it goes up to 39 degrees C.
Okay.
It really cools down the device.
Good. In that case, let me bundle this up.
Yeah, and if you put it in the fourth Facebook page, then when
that I'll drop this
I'll
into
be
the
able to
chat
catch
here.
it.
Yeah, I'm going to get this over there, and SCP-28. I want to copy this. No, wait, there's something missing. Click. Perfect. Okay, we leave this. No, wait, did I leave these running? Did I leave them running or did I stop them? Okay, he's down. He is not.
By the way, I like CM4.
Yes, this thing is nice, easy, straightforward, and whatnot.
Yeah, I like it better than 2012 or all the other 83 or whatever. And for years and years, I used to use Pygmy Force, which is based on CM Force, and I love it.
I bet.
It's so tiny. I used to create applications for work to talk to file servers and get it. I used to be a network administrator. So I write my own little application.
Yes, I introduce myself. Yeah, because the next talk is actually mine, and I would like, there's Pablo. Do you want to make the introduction?
I'm here.
Yeah.
Next speaker, Ulrich Hoffman with Docker Ford.
Exactly. So, yeah, let's see. I share my screen and we will see what it is. So the idea actually about that is I want to use and experiment with lots of different force systems. And so there is this this web page, or let me first get this Zoom stuff here out of the way. There is there's Docker, which is actually the capability to run programs inside so-called containers, which are small, lightweight, well, you can call it virtual machines, execution environments where you can install all the dependencies of a program and the program itself. And when I learned about that, I thought, well, that's probably a good idea to make yeah, to satisfy my desire to try out different force systems. And you describe how to actually go ahead and install a system on a plain Linux system. And then you can actually have it prepared so that it can run in the appropriate environment. And so I started doing this, and let me see, maybe we look at the portable force environment, how these things actually look like. PFE, let's click there. There's a repository called Docker Force under my account, and it collects many open source force systems so that you can make them run on your desktop within these containers. So what a Docker file looks like, it actually describes from a given base system, which in this case is Debian Buster, an older force system, the steps you need to do to install actually the appropriate program or force system in our case on that environment. So what you need to do is you start with Buster, you create some directories, then you do an apt-get update, you install software. PFE is written in C, so you need to have the C tool chain to actually do this, like automake and GCC and make and bzip2 to unzip the directory, and wget to actually get the appropriate distribution. And then what you need to do is to install this. You go ahead and fetch it from SourceForge in this case, and you extract it. And once you extract it, you cd into the directory, and you do some patches maybe to have less warnings. And then you do what you typically do on it with a Unix program: configure, make, install, and then I want to run the container, you have to execute /user bin pfe to actually do that. And let's see how this looks like. If we go to PFE, then we can say make, just make, and this goes ahead. It takes Buster, it downloads the image, and then does the appropriate steps to install all the different things. And we keep this running because it takes a while, and we switch back to the force systems that we have here. So it's actually a nice collection of different systems like GeForce in different flavors. If you prefer to try out something with a 32-bit version with lib foreign function installed or without, this is also for developing on these systems. You go ahead and you see it's fairly old systems. Even the GeForce 64-bit version 0.6 is quite old, but there's also a GeForce Current that we will look like in a moment. And then K-Force is there, and Albert van der Horst systems. And well, maybe we come back to Matrix Stellaris, which actually is an ARM force system. So if you want to run it in a container, you have to supply an ARM emulator to do so. Yeah, and this is what it actually does. And then we have MinForce. We have PFE, MuForce, MyForce. So many force systems I just stumbled on. And also we have commercial systems that have eval versions. And for all of the open source systems, there is also another possibility to execute this actually, or several other capabilities, because the repository is in a way whenever something is modified in the appropriate directories. So here is the list of all the systems. If something is modified in these directories, an image like what we do in the terminal right now is automatically done within the GitHub cloud. And then the appropriate images of the containers are pushed to the repository. So you can go ahead also run here, go ahead and say, well, let's say we want to execute uEForce. then UEForce is the system name that we want to use. And well, this is still running, but well, I just open another terminal and let's see how we do this. I can say UEForce. Run this in a terminal interactive mode, and after I finish the system, please remove the container again. Yeah, this is the environment variables are not set. Docker machine environment. That sets some environment, and I have to eval that in my shell to actually set the environment variables. And once I did this, I can then run this command. And it says, well, on my laptop, the image is not available. So it just downloads the image of the prepared force system and combines it. It does so with some kind of download management and downloads several layers. And it takes sometimes, but it's much faster than building the image on your own. And so what you can do is once this is downloaded and the other things are extracting still, and then we will see. Actually, this download process is only done once because the images are cached on the local system. And I wiped them out just before the presentation to demonstrate this during this talk. So here we go. Actually, it's out there. And here we go. And we have a UEForce running here. And we can make some experiments with it, try it out. And UEForce is the PC version of ESP32 Force from Brett Nelson. Yeah, so that is what you can do right now. Let's see what's happening here. PFE is ready. So it did all these steps that I described earlier. And now what I can do is make run. I have a system on my own. And here we have PFE running with its setup. And I can see words. And okay, this is a primitive one. Whatever, lots of primitive things. I don't think that PFE has any high-level words that are not defined in the system kernel right now. And yeah, anyway, you can say make to create the image. You can say make run, also create the image locally. You can say make run to execute the force program, and you can make xlerp because there is a source directory. And within this source directory, there is a file xlerp.fs, which is some simple test program that just says hello and then defines a loop and let it run. And that's interesting to see if you can and how you need to do what you need to do to actually make it run on a specific system. Yeah, so make xlerp actually does this command line, and PFE expects a file name on the command line, and that's the one that you would use. So you have connection to the local file system if you want to. You see it's a little bit more complicated. You have this -v option to actually map the container directories or some of the container directories to local directories on your system. Right, so what we can do, and so now that is probably interesting, we go to GeForce current, because, well, as you probably know, there's an ongoing GeForce development, but the archives that you find are more or less outdated, like we saw 0.6 something, and if you get installed GeForce on a modern Debian Linux system, you get an outdated version, but you want to have a new one. So I already did before a make to create the image. So it's very fast right now to have the image. And if I say make run now here, then it starts, and it's the version from 8th of February this year. with all the nice things. So you can see words and use the debugger, and you see the color and the status line. So if you put something on the stack, it will show up down there, and you can do the appropriate calculations and whatever, and use GeForce in this way. You can also say make xlab, of course, to use the xlab file. And you see it's GeForce is invoked in a different way. You provide a file name, and then you, with the -e option, you can add additional force words that get executed after that. So if you just want to run this file, you do it like this. Right. So this is if you want to use this on your local machine. You have to install Docker, of course, the runtime that allows you to execute these containers. But if you don't want to do that, there is another way that you can do. And if you go to the repository, let's see, how can we go to the repository, to the top level? You see this green code. This is where you normally clone the repository. But it's, for some time now, it has also this tab. It's the code spaces. Yeah, and this is a development environment that you can use that works in the browser. It actually hosted on the GitHub cloud, and so you can actually go there. And I already started a code space. And if not, then you just see a green button here and start a code space. You have to be logged in with your GitHub account. But if we go there, then what we get is hopefully not another one. Yeah, it works. You get a instance of Visual Studio Code that runs in the browser, and that gives you access to the repository and to appropriate the appropriate files. So here you see you get the README and the appropriate preview, and you can go ahead, and it gives you a journal. Just do what I did without installing anything. Yeah, you can just go here, and we can go and say, well, let's go to PFE and do a make. There's Docker installed in that development container. So you can just go ahead and do what I did just on my local system. You can also do in the cloud right from the repository, where you say, okay, open a code space. And then within that code space, you can try out all these different systems. One thing that the repository supplies is these prepared images that you can just run with a command line that I showed earlier. Yeah, like docker run -i-t, and then you say you prefix this with docker run docker force. Then you don't need to build them inside this development environment. The exception is that the commercial systems, I don't provide any images for them because of legal reasons. I don't think the vendors are happy that I will provide images of their systems on a publicly available platform. So they want to have control about their evaluation versions or whatever. But what you can do inside this, well, maybe we just break it. We saw this earlier. We go to VFX, for example, VFX. And let's have a look at what the VFX description actually does. Here's the Docker file. Very similar. It starts with Buster, and it goes and fetches the VFX force eval distribution from their website. And for the moment, it builds it so that you can run it here. So let's see how this works. And if I say make here, then it will go ahead, use Buster, do an appropriate update. Because the vendors provide their system in binary, there is no need to have a C toolchain or whatever installed. You just want to run the environment there. It downloads the eval version of VFX. It does it, and it creates the appropriate installation. Does the installation step that you normally do when you read the README file and say, what do I need to do to install the system, which is essentially go to the VFX directory and invoke the install me lin32 shell script, which then does the magic and installs it in the system. But the system currently is the Docker container that we're creating. So once we did this, we can make run. And there we are. We have the quite up-to-date VFX system, right, downloaded from the eval website. I don't know why it's ended in 2020 with a copyright. Anyways, so we're just leveraging the available eval version, and the contribution of the Docker Force repository is actually that all the necessary steps to install this or this or this system has been captured in these Docker files. So you don't need to figure out or read documentation. You can just go ahead and do this. And maybe finally we go to Makrisp Stellaris and also have a look at that. What is the Docker file for Makrisp Stellaris? Very, very simple, as you can see. And why I discuss this, let's see, we make this image. Yeah, just make. What's going on? I don't know. Anyway, yeah, let's see what the makefile looks like. Aha, it has some debugging rules in it. So what we need to do is make image here, which normally is the first target. So let's have a look at the Docker file. It starts with Debian Buster. Well, all these Docker files have been prepared some time ago when Buster was actual. So today you want to use Bullseye probably, and maybe Bullseye Slim to not have all the non-needed packages installed. It installs QEMU and wget to get the binary of Makrisp, and then it goes to SourceForge, downloads it, and expands it. There's nothing to build, yeah, because Matthias Koch provides the binary of Makrisp as well. Otherwise, you have to assemble it. So yeah, and you see this is what happened, and now we can just make run. And tada, we get Makrisp Stellaris, which is an ARM4 system running in this container, and we can do words. Yeah, and we can figure out that if we want to do a variable, yeah, say variable x, well, this doesn't work because Matthias decided to have variable in a figforce style, where you have to supply an appropriate value, x, and then you can say x fetch dot, yeah, and 55 x store x fetch dot, and 7. What do we say? Minus 13 x plus store, and then x fetch dot web dot. Wow, the answer is 42. Great. Yeah, so I think I would encourage you to have a look at this, give me feedback. If you have a Force system that you want to see on the Docker Force webpage, being able to run. Docker actually typically supplies a Linux environment for running these programs. We could do some stunts with Wine that we install inside the Linux container, and then try to execute Windows programs as well. But so if you want to see some Force system in there that I didn't find yet, then just contact me. And if you find any issues, then yeah, also let me know. I would encourage everyone to play around with this and see if it works, and give me some pointers to what any issues might be. So yeah, that's it. So you can use any of these 4 systems with a single click, more or less. Thank you very much for listening to my talk or my presentation.
Thank you, Ulrich. Very well.
Excellent. Excellent.
Right. Any questions?
Not a question.
Where's the address of your GitHub?
Where my GitHub is, yes, of course. I paste the link to the repository in the chat. So where is it? There's another one. Okay, here we go.
You know, the operation system I mentioned is totally based on packages and containers. It uses Docker. And one of the things that I have on my schedule was to try to figure out how to create my own Docker containers, because I have a bunch of force. And if I create them as Docker containers, it'd be easier for the system to deal with them.
Yeah, that's right.
You know, well, you saved me a lot of time here.
Yeah, thanks, Alex. It looks like the same URL. Great, yeah. And now you have lots of blueprints on what you need to do. There are some systems that are right tricky, like the 386 versions. To make them run on a modern 64-bit system, you have to add i386 support and the appropriate libraries and so on. And you find the recipes how to do that also in the appropriate Docker files. Yeah, so there's this 32-bit GeForce, and that was actually really a stunt to do that, where you have to do install the multi-architecture support, and then also the 32-bit things. Yeah. Any other questions?
Yes, I have a question.
Yeah.
Do the Docker run on any platform or just x86?
Yeah.
I mean, would they run on Raspberry Pi maybe? Or
my
future version?
Yeah, my understanding is, well, the containers share all the kernel of the surrounding system. Yeah, so also the execution environment, more or less. The containers are more or less shields from managing access, process and file system and memory access and so on. So there are different flavors of containers. So on in a Windows world, for example, you have containers that run the Windows execution environment, and then you have Windows-like containers. And on a Raspberry Pi, which has an ARM CPU, you get Linux, but it's all ARM binaries, which if the system is actually written in C or so, then it wouldn't make a difference. So GeForce and PFE, for example, you would just compile on the Raspberry Pi and have ARM images and then to execute. That would work. I think there is Docker support for the Raspberry Pi, but the images are not interchangeable.
Right. Okay, I will definitely have a look at your repo and maybe try to do a pull request to add Alex Forth to it.
Yeah, great. I look forward to that. Right.
Ulrich?
Yeah.
You're probably the right person to answer a question I had on my mind for quite a while. What's
Go ahead.
main difference between Docker and a VirtualBox machine?
Yeah. Right. A virtual machine. I said containers are some kind of virtual machine. Well, it's a virtual execution environment, but the difference is that containers are more lightweight and they use the operating system kernel of the underlying system. Whereas a VirtualBox, virtual machine, is actually using whatever it emulates. So you can run a completely different system, like a Windows inside a virtual box, virtual machine, which has a Windows kernel. But if you have a Docker container, that it always uses the kernel of the underlying system. So if you run on a Linux x86, your containers will be x86 Linux containers. Yeah, and they all share the same kernel, and that's the main difference. Yeah.
So the Docker runs on the hardware that you have.
Yeah, and the kernel is not emulated, whereas with VirtualBox or VMware or what have you, Parallels, the hardware is emulated. The CPU in some hardware-supported virtualization mode, but it also emulates the operating system kernel, or runs the operating system kernel on the virtualized hardware. And that's with Docker, that's not the case.
Okay, thank you.
You're welcome. All right. So thank you very much. And I skip over to the schedule. So next speaker will be Virgil, and we'll learn more about Collapse OS and Dusk OS, sorry, and the C part, tokenizing and things like that. Virgil, please go ahead.
Yes, hello. So yeah, the last presentation we saw the harmonized assembly layer. Now we're ready to dive into the C compiler. So yeah, so today I want to cover the whole process of compiling a C file. I'll go over tokenization and expression parsing, because that's quite a big subject. So I will share my screen. Screen. Yeah, this thing here. Yes.
Right. That works.
Do you see? Yes.
Yes.
All right. So in the previous presentation, I was using emulation, QEMU, to emulate Dusk. But since the last presentation, there was a new development in Dusk called user mode Dusk, which allows Dusk to run natively on the system. So that's user mode Dusk in its curse flavor that I'm going to use. So you all see this. So my machine is an i386, is an Intel CPU. So this user mode Dusk is running in i386. So the C compiler. So I have this this file. Oops. All right. So I have this. I have this file that is a simple C function that I call my adder, that simply adds A and B, and I'm going to compile it, because before I talk about the tokenization and the expression parsing, I just want to show you how we compile a file, on a C file in Dusk. So we're going to load the compiler. All right, and we're to compile a file. It's you use that word cc bracket and then the name of the file to compile, and that will create a word that is called my adder that I can use this way. All right, so this so the compiled C file is the compiled C word can be used as any other fourth word. And you know, in the previous presentation, I was making extensive use of the disassembler to show the result of my of what I was doing, and I'll do the same here. So I'll load my disassembler, because as I was telling you, this is so this runs natively on my machine, but it's an i386 machine, so what was compiled was I386 code. So if I do my adder this, we will see that the code here that was compiled is rather straightforward. So if you remember on Dusk, ESI is PSP, ESP is RSP, and EAX is top of stack. So in all C words, I extensively use the work register, the top of stack as a work register. So I always take some wiggle room. I make some wiggle room here with the dupe so that I can use EAX freely in further compiled word. So every C word starts with this, and then my parameters that were supplied here end up in ESI and ESI plus 4, and this is exactly what I do. I do a move of ESI plus 4, which will be 12, and then I add to it ESI plus 0, which will be 23, and the result ends up in EAX, which is top of stack, and all I need to do afterwards is to nip those two parameters that I've just received and return. So what I'm showing you is a bit like what I was showing you when I was telling you about the HAL. It's pretty much the same thing. So this is how functionally the C compiler works. And now I'd like to dive in with you as to what mechanisms allow us to compile the C file. So to show you that my compiler is modular, I'll restart Dusk so that you know that we're running on a clean slate here, because I will load parts of my C compiler to tokenize and to parse expressions. So first of all, tokenization. So we'll show it right there. I'll open the file here. All right. So you'll remember that this is the C file that we're trying to tokenize. So let's tokenize it, and let's start with a naive approach, which is to just use Word. So what if we tokenize this with the word? So it would look like this: spit tokens, spit tokens, and it would look like this. And wait, I'll write it and then I'll explain it. While word. All right. So this would be this. So what this does here is that it checks if there's a word in the input stream. So as long as there's a word in the input stream, it loops, and then it gets a word, and then it types it, and there's a new line so that we can see how tokenization happens. So now we can do this spit tux. So the exact word here is in Dusk. The input stream is very easily overwritten, so we can hijack the input stream how we want, and this is a feature that I use a lot in Dusk. So what this does is that it hijacks the input stream with the contents of foo.c and calls spit tux, which means that when we call word, our input stream is this. So, and then as long as there's an input stream, we'll loop, and then when we stop looping, when the word returns, then we close the file and we're done. So what happens here is that I read word, and we see that there's a problem here, because my word boundaries of fourth don't work with C, because the tokenization is C has to know about the symbols it will read. So to do tokenization in Forth, then we need to build a tokenizer. So so this is what we're going to do. In Dusk, I have a general purpose tokenizer, which is in a ComTok. And with this is just an API for fancier tokenizer that will go over it. And this API looks like this. Q while s type. All right, so this is the same word using the tokenizer API, and this is the important word, that is go fetch the next token using whatever method has been installed, and unless there's nothing to consume anymore, in which case we yield 0. So that makes this thing work. By default, the general purpose tokenizer is the equivalent of word. So if we repeat that thing we've been doing, we will get the same result because the generic tokenizer is a word tokenizer. However, we have a C tokenizer here that we can load. And now I won't show you the code because showing code in a presentation like this is meaningless, because it is anyway. I won't show you the code, but it's like 70 lines of code or something, so it's rather simple. And so what we'll do is that we'll tell the system that we'll tell the general tokenizer that we install the C tokenizer now. So we'll repeat the same step, and we will see that tokenizing works as expected. So when it fetches my adder, then it detects that this is a symbol, and it says, oh well, my identifier is done, so I'm tokenizing the next word, and so on and so on. So this is how tokenization work. We can try some fancier tokenization. For example, now for this I'll need another tool. Right now I'll tokenize strings instead of tokenizing a file. For example, if I use spittox on a string that will be A+++B, you will see that that my tokenizer works properly. You know, because this is a typical problem when you try to tokenize C word. That is, which plus do you add? So what is A+++B? Is it A++ space plus space B, or is it A space plus plus space? Anyway, so which one is it? And the rule for tokenizing is to be greedy. That is, you get the biggest known symbol that you can, which will be plus plus, and then we'll have the plus. So exec bracket is the same as my previous exec, except that it executes a range in memory, which is my string here. So as you see, it tokenizes properly. You know, it tokenizes the A, and then the plus plus, and then the other plus, and then B, and then the semicolon. In Dusk, the tokenizer also manages macros. So macro is done at tokenizing at the tokenizing step. For example, let's say that I define a macro foo that does foo42. Then if I tokenize this spittox, and I've tokenized something like this, at plus exec, we will see that the macro is hijacking the input stream to then input itself into the tokenizer so that it's exactly the same as if I had typed this directly. We see that tokenizing works as expected, and we don't improperly consider this as a single token. So that's my tokenizer. And any questions so far about tokenizing? No? Am I going too fast, or am I understandable?
Yeah, I think so.
Fine with
All right.
me.
I finally understood what tokenizing means.
Does
All
the
right.
does the tokenizer yield quoted strings as a whole unit? So if you have a string between quotes, it will get one token out of it?
Wait, I didn't get the question. So the tokenizer yields strings, where the result of
but
a
if in the
single token
C# file there is a string surrounded by quotes, will the whole thing be a single token?
Yeah, we will. We can try it. So spit tokens, a string, and then my str equal a quote. Now I have to escape my quote in my string. So that the escape there is for the escape there is for this literal here. All right. Hello. All right. So this will be a single token. Oh no, wait, I hit caps lock. But this time, because I'm in user mode disk, I can copy paste. Oh no, I forgot to close my string.
Yeah.
It's not supposed to be does, but I don't know why. I haven't tested it first, but it's supposed to give a single token.
Yeah.
But I can't answer your question because I'm not sure what happens there. But it works as expected when all things considered, the string is ends up as a single token. So I'll continue with expression parsing. So when all right, so when we need to generate code for example, to generate the code that goes with A plus B, there's a problem. The main problem here is that this expression is an infix expression, and we need to apply complex rule related to operator priority and associativity and stuff like that. And this is a complex problem, and I think I came up with an elegant and simple solution to tackle that problem. And this is so this is what I'm going to show you. Oops. All right. Wait, I need a little helper word for this. I'll explain you why I need this as I use it. All right. So how do we understand this expression? Well, my approach is to reorder this expression into something that Forth likes, that is a postfix expression. So for example, here, what it does, so it tokenizes every element, and then it reorders it into something that forts understand. That is, we push A, we push B, and then we apply plus. So why did I need show here is because the token expression parsing works by checking, by consuming tokens as long as it can build an expression. So it always needs to look forward. So that's why we need this semicolon here. It's to tell the expression parser that we're done with the expression. And then if we don't drop the last token, then the token will stay unconsumed into the token queue, and it will mess up with the next expression I'm going to show you. So this is why I needed this little helper word there. So this is the general approach, and I call this sequence expression. That is to transform an infix expression into a prefix expression. So yeah, that's why I call this sequence. So of course it works with expressions that are more complex than that. For example, A plus B plus C. So oops, minus C here. What? Right. So we see that it does the expected thing in Fort, you know. So if we wanted to translate this expression to Fort, then that's how we do it. It manages priority correctly. For example, if we go with A times B plus C divided by D, then we see that wait, A times B plus C divided by D. Yeah. All right. So we see that that priorities are respected. That is that the multiplication operator has priority over the addition operator. So this is how you'd expect, and we see that parenthesis in this thing works as expected. So for example, A times B plus C divided by D. We see that here parenthesis properly overwrote the natural priority of binary operators. Now things get murky when we add the unary operators in the mix. Oh no, before I talk about unary operator, I just want to show something about assignment operator. B plus C. There's something weird with assignment. If you try it at home, you will see that assignment operator are generated in the opposite order, and there's no great the reason for this is to help the code generator generate code in the proper way. So when I go to the code generation part, you'll see that it's a lot easier. It makes the code generation part simpler if we generate the right part of the assignment before the left part. So I've inversed the sequencing on assignment operators. So that's why it's this way. Yeah, see. The unary operator also works as expected. So we see that we get into tricky tricky edge cases. Well, it's not so much of an edge cases because when you write C, you write that kind of stuff often. But in terms of parsing an expression, it gets complex there. And if you're using a naive parser, then you're going to get to some hair pulling in that kind of expression. But this is sequenced properly. So in this case, we start with pushing A, and then it's a binary expression. So we enter the second term here, and here we see the subscript operator is the same as a plus and a dereferencing. So this should be seen as a binary operator here, and we see that here the minus C here is generated, is sequenced as this, and so we push C, and then we apply the unary operator minus to it. And the U prefix here is because there are name clashes in the operator, so we need to be able to differentiate between them. And I had a couple of. Do I have time? I'm feeling that I'm using a lot of time. Function calling is interesting. I'm doing function calling, and then I'll stop. All right. Function calling is tricky because we need to push arguments to the stack at definite points. For example, here to call foo with those arguments, to sequence this, we need to push 42, and then we need to tell the compiler, we need to tell the code generator to push it right away to the stack, so that we don't deal with it with the expression anymore. It's pushed away for the call. So this is what happens there, but and it happens in reverse order because of the calling convention in Dusk. So all arguments are reversed during the sequencing. So we begin with a call to bar that has no argument. So this is the operator for function calling, and this is the number of arguments that will be consumed by the call, and then the name of the identifier. So we call this, and then we push the result of bar, and then we push 42, and we don't push this one because this is the last one, and this is a technicality. We don't need to push the last argument, and then we call we call foo with that will consume 2 arguments, and we assign the result to the identifier A, and that's my sequencer. And I'd stop there because I'm done. Do you have any question?
Right. Thank you very much. Are there any questions?
I think it will be mostly a comment. I'm really glad that I'm finally getting to the compiler integrated to Dusk OS, because this is what impressed me when I saw it first. And I'm starting to understand better how a compiler works.
Mm-hmm.
I might have a question. Does a real compiler in C operates the same way? It has to convert infix notation into postfix. Does it do it, or
Well,
is it
this is a very interesting question that I would, because when I look at the other compilers, I see that no, they don't seem to do that. They seem to go the way of complicated code. So this development here that I've just shown you is very new. I did it last week. This is a big refactoring of my C compiler that I did last week, and I think that what I just written there, this sequence expression thing, is something that can only be done well in the Forth environment, and that is way simpler than whatever TCC does. TCC is very complex. Or there was on Hacker News there was an article about from Crafting Compiler that was showing how we do expression parsing when you follow some whatever academic paper that was released by whatever dude from whatever university, and when you read that, it's overcomplicated. This is really simple compared to whatever is the norm, and this is an open question I have for everybody. This is super simple, and I don't know if anybody does that.
I think in some way you've just proven that the postfix is a better way to do things.
Yeah, but I've been trying to think what it would take to bring this approach into, for example, a C compiler written in C, and you'd kind of have to re-implement your own forth to then generate the code that goes with it. Whereas where you're in Fort, you have your Fort. So this is the simpler approach.
Yeah, I think there's a book called the Dragon Book, compiler design book that used to be standard text, and I mean there's a whole bunch. I mean there's a whole bunch of different steps, but I think a lot of compilers do effectively convert to postfix. I mean they're not in a text-based format, but a lot of them do sort of have to transform an infix expression with brackets to a set of operands with operators applied to them, and that sort of ends up as a postfix.
What I've seen is that. What I've seen is not that. What I've seen is you transform into an AST, and then but the AST doesn't give you ordering. So, for example, if you have A plus B, so you have a nice structure with a tree, and then with plus, and then the first term is A, the second term is B. But then, so what I've seen is that the code generation part will dive into a recursive manner and stuff, and do the prioritization while it generates code, or maybe it will reorder nodes into the tree or something like that. But this is not what I've seen in the wild. But yeah, maybe I haven't seen enough.
What you often do is that you use the internal representation that you build up then to do optimization, like inlining or that code elimination or things like this. And so if you just parse and generate code directly, then you have a hard time to actually do that. But it might be just fine to have a compiler that parses and tokenizes and then generates code.
Yeah,
the immediacy is great.
Yeah, I mean, obviously some compilers, depends where they put the optimizers as well, and because obviously multi-pass, with LLVM, for instance, but some of them can eliminate expressions, and it depends on what level of optimization they're doing. Backends will do, register coloring, and they'll try to use as many registers as possible and keep those registers active as long as possible. So I mean, it depends what you're trying to do, and it becomes, you ideally want to simplify the expressions. I mean, some compilers, for instance, will entirely eliminate loops. For instance, in C, you can assume that any loop is not infinite. If you've got an infinite loop, which we often have in embedded systems, for instance, technically, according to the C standard, you can eliminate those loops. So they can. There's a whole bunch of transformations they're trying to do as well as at the level. So it's a very interesting subject, but it depends how deep down the rabbit hole you want to go. Often simpler is more effective, because correct code is always better than incorrect optimized code.
Yeah, of course, but so of course being a direct generation has its drawback with regards to the optimization that can be done. But I still do, for example, constant expressions are evaluated at runtime in Dusk C compiler. So there's a bit of optimization that I don't need an AST to do that. I can do it on the fly as I generate code. But yeah, I can't go as far as an AST. But the simplicity that I get by foregoing a bit of optimization, to me is astounding.
I agree.
When I first got started with computers, I was really interested in compilers and code optimization and code generation and all these things. So I read a lot of books on it. And then when I learned about force, it totally blew my mind how simple it could be. It seemed like the academics just loved complexity for the sake of complexity. And all I did was peephole optimization, but it was so much simpler and faster.
Yep.
All right. Any other questions, comments? Thank you very much. So very interesting indeed. All right. So I guess then I will introduce the next speaker, which is Sven. And I actually, to be honest, I don't have an idea what multi-port gates will be about, but we will learn about that. And so I'm very happy, Jos.
Yes, thank you.
Please
I would
go
like
ahead.
to share a screen to explain that new feature.
I see your screen. The black Windows desktop.
You see my screen and my voice is clear?
Yeah.
Okay, thank you. Well, the multiport gate is actually two variables that can be used to make a decision depending on multiple conditions. It uses in fact the bits of a variable to do that. The first cell of the two variable contains the inputs. The second cell contains its properties, that are things like the threshold and the number of used bits. The output appears on the stack after running the query. The main advantage is that the multiport gate has only to compare one value to the content of one variable to make a decision, instead of having to check a number of separate variables, and that is actually very important and very useful. All inputs and outputs are easy to track. A simulation is also possible. There's less chance for errors, and it is also creates a compact code. It runs on any ANSI board with a structure pack. For the usage, the first thing you have to do is to create two variables, and then you have to enumerate and name the input bits. Let's see how that works. Oh, sorry. This is the source of the multiport gate. Even kijken. At the end, I made a test case, so we can see how this works. I will compile it now in Win32 Fort. And if you want to create a multiport gate, then you have to create a two variable. That's done by now. The address of the multiport gate is important, so I put it on the stack. And I show it to you. The next thing we have to do is to create the next thing is step 2, and step 2 is to enumerate and name the input bits. That can be done with B input, and B input is actually a shortcut for bit input make. And bit input make needs a bit number on the stack, the address of the multiport, and next it will need a name in the source. When it is done, it will return a bit number that is increased and the source of the multiport gate.
Sorry, Joe, I think there is one screen that we don't see.
Oh, what do you need?
What you're explaining, we don't see it.
Oh, sorry. Thank you for saying that. I guess you do not see this screen. Do you see the source of the
Presently
multiport?
here, I only see a slide.
No, I can see Win32.4 IDE and Win32.4. Oh,
Yeah, I see both windows.
yeah, me too.
Okay.
Oh, it's
So
one
I'm the
system.
only one that's seeing. I see a black window on the right with nothing being typed in.
That's weird.
And now?
Me too. I see a black window on the right.
Oh. Yeah,
Not
that
too
is
bad.
hard to solve. Is it one question? Anyone else a problem with the screen?
I see okay, your screen looks like a complete Windows 10 desktop. I see your local time at 1618. I have the start menu down there on the left. And I have a Win32.4 IDE window and something further to the left that looks like a Win32.4 console window.
Yeah, this is you. Even kijken. I will see. Now on the left should be Win32.4. Is that right?
Yes.
Okay.
Yes.
On
Yes.
the right side, there should be the EDA.
Yes.
Yes.
Okay. Okay. So, are there more persons with a problem with the screen, or is it only one person?
It was showing me the blank, just the one window with the black on it, but it took a while. I think it might be a bandwidth issue on my part.
So, okay. I can continue, I guess.
Yes.
Okay.
Yes.
Thank you. Where were we? Oh yeah, the first line. I was at the word I present. I present is actually a shortcut for the input present, which I'm going to define. Let's define 3 input ports. That's done by now. The next step is to store the properties. The first value is to store the number of used inputs. And as you see on the stack, the 3, and that means the number of bits has been increased to 3. The address of the multiport is also on the stack, and that's also needed to store the last property. That's the threshold. In this case, it must be 3. Okay, now we have defined the multiport gate. We can also see what the multiport gate contains by using .inputs multiport. And here you see the inputs of the multiport gate. They are all off. And then it is possible to fill the to set the inputs. Words defined with bit input make return on the stack the input number and the address of the and the address of the multiport gate, as seen here. Setting an input can be done with bit input store. That's this line. You simply put the flag on the stack, the input number and the address of the multiport gate, and then the input store will put it on the right place. There we go. And if we look again at the multiport gate, then you will see that the first bit is filled with a 1 and the other two are still 0. The other way to fill it is to use bit put on or bit put off. Let's fill 2 more and we put 1 into it. And again, the multiport gate can be seen and all the bits are 1. The next thing that you can do is execute queries on those bits. Example, you can sum them up with sum multiport. And if you do that with a dot, then you will see what happens in the multiport gate. In this case, all values are still active. The threshold was defined at 3. The activation value is also 3. That means it's more or equal than the threshold, so the output is activated. In the source, you use also some MP, but then you don't add a dot. Then you get a number -1 on the stack, and that means the multiport is true and the output was put on the stack, and that is the thing you can use. The words with the dot are only there to see what happens and not for use inside a source. The next query is match NP. And I use all bits in this case. And all bits, that means it fetches the value of the property number of inputs to determine what the value will be if all bits of the multiport gate are true. And that's much faster than sum input, because sum input uses do loop to check for all the bits and to send them up. Oh, sorry. Okay. Here you see what happens. All inputs are still 1. The input value is 7. The match is also 7. So the activation value is true and the output is activated. The last query you can execute is any MP. Any MP is true as soon as one of the bits is 1. There we go. All inputs are 1, so the input value is 7. Any returns true. The activation value is true, and so the output is activated. And in the source, you would use that query without a dot. So you get 1 number on the stack. In this case, true. Even kijken. It's also nice to see what happens if you put all inputs off and activate that query again. Now all inputs are off. The input value is off. Any says it's off, so the activation value is off and the output is also off. That's about the usage of the multiport gate. The next step is to put a number of multiport gates in a network. In this case, it's off. In this example, This example is used to control a window with 3 multiport gates. The multiport gates Atom, that's this one, is used to control the window automatically. The multiport GUI is used to control the window manually. Their inputs are used as their outputs are used as an input for the multiport out. The multiport out controls the window. The inputs automatic and override make it possible to switch between an automated way or a manual way. So it's actually using a GUI. Even kijken, waar is het? Let's see how this works. This is the source of the simulation for the examples. At the start, you see 3 variables. Dus that means there are 2 multiport gates defined. The next thing is init net that is used to start with a clean system. So all multiport gates will be off. The next word is set override. Set override works as follows. It reads the input automatic and puts an inverted value in the input override. So there is a relation between Atom, multiport, and the GUI multiport. Then there is a word evaluate window net that updates the relations, and the result which you get back on the stack will open the window. The first line uses set override. The next line looks if all inputs are true for the multiport Atom, then passes the output to E Atom of the multiport out. And that's over here. The third line looks if all inputs are true for the multiport GUI and passes the output to the input port GUI of the multiport out. That's this here. And the last line, then the multiport out is used to get the result on the stack by using the query AnyMP. Okay. Now I'm going to compile the source to see what happens. If we execute .eval window net, then we see how the network looks. The first one, the first multiport is Atom. All inputs are off. So there's no match. The output will be off. The GUI, there's no match. Again, the output is off. And out gets no input. So the output is off and the window will thus be closed. If we change the number of inputs and we put them on, and we also change the automatic control to on and see how the network looks, then it's another story. All outputs are on, including number 6, that is the automatic control. In this case, there is a match, so the output is activated. The GUI is not used, so the output is off. Out gets 1 input, so any will be on, and the output is activated, so the window will be open. It's of course possible to change 1 input. For example, we change the temperature and we change it to off. Now we can again evaluate the whole network. And there we go. The atom, the multiport atom has no match, so it's off. The input, the manual input is still off. And so the output gets no input. So any will be out, any will be 0 and the output will be off, so the window will be closed. That is how a network works. Even the code is quite compact. If we look at set override, it contains the input automatic and the input override, and then it inverts the destination. Well, it's only 3 4 words, and the input automatic and input override put the input number and the output, and the address of the multiport on the stack. So we got in total 4 outputs on the stack, and then invert destination output changes the output of E override. Okay, well, there's also a download for over the internet available. I will put it in the chat so you can download and play with the system. Even kijken. Chat, Mr. Chat. Oh, daar is hij. There we go.
All right. Thank you very much.
Okay. Are there any questions?
Huh?
Are there any questions? Okay, then I will.
Yes, sorry, I have a question.
Okay.
Hi, Josh. Yeah, I enjoyed your presentation very much. What was your motivation to come up with this? I don't know how to call it, data abstraction, I think. Does it come from, and there is some kind of, I think, inspiration from the hardware, I think, right? Like OR gates and this kind of thing. Isn't that right?
No, I was working with my home smart home system, and I got at some time a problem. I noticed that I was actually, I was actually having a problem. I needed to compare a number of inputs and then make a decision what to do with the device. And when I got for the second time the problem, I decided to do it another way. And later I was studying some AI, and I thought, well, that's something I can use. I changed it a bit, and I don't need all levels as in an AI. And I got to the bit level at last, and that's how this came to use.
Okay, yeah, I've got a second question, if you allow me. So in your implementation, you store each bit in a bit or in a byte? I mean, is there any kind of memory limitation that?
All inputs are put in a bit.
Okay.
And that's why I only have to use one value.
Okay.
And only one time have to compare it.
Okay. Thank you.
All right. Other questions to Jos? No, then thank you again. Great talk. And let me look at the agenda. Oh, we're done with the talks. And here's the agenda says live demos and workshops and chat probably. So I think what we can do is we can officially stop the recording and open the informal chat session for whoever wants to stay and for how long we actually want to have it.
Yeah, but I think we should thank all the presenters as well today. It was a lot of very good talks, I think, and had me looking up many things, leading me down many rabbit holes. So thank you to everybody who presented. It was really great.
Yeah, thanks. And the idea is to have something like a Force Cafe in March. So no presentations, but of course workshops and hands-on and demonstration or whatever, but without a formal schedule, but just drop in and talk and show what you want to show. So self-organizing. And in April, we will have a scheduled meeting with talks again. Okay. Then I stop the recording, which doesn't mean we say goodbye. Here we go.